Good morning, everyone. So welcome back to QX01, Introduction to Quantum Information and Associated Technologies. So as usual, let's have a look at the program with some changes, as usual. So today we're going to talk about quantum gates. We will also finish some of the aspects that we haven't covered last time. Next week, there will be colleagues from the British startup company called Qubits, and they will have a lecture on quantum cryptography. It will not be live, but it will be available on the UTT YouTube channel afterwards. It will only be live for our UTT students. Then 2 weeks where there will be no lectures. The week after that, so there will be a midterm exam. And after that, there will be holidays. And after that, we will resume with quantum algorithm and quantum parallelism and so on. And in particular, we will have colleagues from the INRIA, Thales, and Atos coming to discuss some of these aspects of quantum technologies regarding quantum sensors, more algorithms, and also an introduction to the Atos quantum learning machine. Right, so let's have a look at the program for the day. So 5 points today. Quantum gates, so we have been talking about them a little bit. Now it's time to go into them properly and to see what we can do. So for that, we'll start to introduce the so-called 1-qubit gates, where we already saw them. They are mostly the Pauli Matrices. And then I will talk about 2-qubit gates, and I also mentioned it briefly before, in particular, the so-called control NOT or C0 gate. Then I will briefly mention gates with more than 2 qubits, with 3 qubits, namely the Toffoli and the Fredkin gates. Then we will go on into how we make quantum circuits with these gates, how we put them together, and what are the rules. There are some rules that some of them we've seen, some of them we haven't yet. And then I will talk about a practical case. In fact, I will talk about 2 practical cases, one being the creation of a Bell state with quantum circuits and how we do that. And the second one, I'll spend a bit more time. I will probably not be able to finish today. We'll finish it next time, but that's fine. The case of quantum teleportation, which is very nice in many aspects and makes also people sort of dream about teleportation, perhaps. Right, before that, as I said, we are not quite finished with last time. So there are two aspects that we need to finish for today. The first was on the mean value of an operator and the notion of commutation that we haven't had the time to finish last time. And then the other point will be to talk about the so-called outer product, which I briefly mentioned before, but we will finally see it today. And outer product as opposed to the inner product, the equivalent of the scalar product that we already saw. So last time I wasn't quite finished with the mean value of an operator. So if you remember, what we said is that if we take an operator A, and we said that to an operator, what we mean by that in quantum mechanics is we mean a measurement, or at least an apparatus that can make a measurement. Then we end up with some results, which is the eigenvalues AN, so the measurements, the results, when we make this, when we apply this operator A, and the eigenvectors, so the quantum state vectors associated to it, AN. So in other words, and I took the example of a spin, of a 2-state spin. spin of an electron. So, which can be up or down, or we said it can, which is the equivalent of spinning in one way or spinning the other way. So in this case, when we do not know, the wave function of the system is simply the sum of all the possible all possible quantum state vectors. So in this case, in the case of a electron spin, then we would only have two vectors, an, one would be up and one would be down, with two, as we said already, two eigenvalues associated to each of these eigenvectors. So in general case, the wave function, or the quantum state vector of this object, will be a superposition of all the possible eigenvectors. So in general, it would be the sum of the Cn an. So if I write this, so A is the operator, then we have eigenvalues an and eigenvectors an. And so in general, the ket wave vector will be a superposition of all the different possibilities. So for a qubit, there are only two possibilities, 0 or 1. For an electron spin, is also up or down. But you can measure other quantities which can have, like the angular momentum, for instance, which can have more eigenvalues and more eigenvectors associated to them. So in general, your wave function before a measurement will be just a superposition of all the possible eigenvectors. So now I want to define the mean value of this operator, which we write like this. And the mean value can be seen as the probability Pn, or the sum of the probability Pn of obtaining an. So if I take a coin, for instance, so P1, or P1 would be the probability of obtaining head, that would be the result, and it would be 1/2, and P2 would be tails, which would be A2. So we can write this. So example, a coin with heads or tails. Okay, so for French people is pile ou face. All right. And in this case, we can define P1 equals 1/2 to obtain heads, say. So that would be the result A1. And P2 would also be 1/2 to obtain tails, which would be the A2 result. Okay, so it's not difficult to see that the average of an operator is going to be the probability Pn of obtaining the sum of the probability Pn times the eigenvalues an. Okay. But then, on the other hand, if you remember, we said that the probability Pn, this new device, I have to get used to it. So the probability Pn is in fact, so Pn, probability, and that's what we saw that for a two-level system for qubits. The probability for qubits, so if we had 5 equals 0, alpha 0 plus beta 1, we said that the probability P alpha is alpha squared of obtaining the result 0, and P beta is beta squared of obtaining 1. So by the same token, we can expect that this quantity squared would be the probability Pn. These coefficients in general are complex numbers, like alpha and beta in the case of a qubit. So it means that this is Cn star Cn. And if I do that, then I can identify this relation. So that would mean A, mean value of A would be sum of n Cn star Cn An. And now what is interesting is to compute this quantity here. And you will see that if I compute this quantity here, I will find exactly this result. So let's do that. So now I define the mean value of A in the wave for the wave function of the system to be this, so the bra operator and ket. So let's see what that does. So let's leave this one out for now. So that would be A applied to this quantity, so sum of n Cn An. Let's take some colors. So no, maybe not green. Pink is nice. So this is an operator. This is a sum operator or matrix as well, remember. It's a matrix. So we need to apply this matrix to this ket, to this vector, quantum state vector. So that would be psi, and then sum over Cn of An. But this is exactly applying the matrix, so the operator, the measurement, the apparatus to the quantum state vectors that are its own quantum state vectors. And this would be the eigenvalues times the eigenvectors. So this would be An, vector An. So, okay. Then for this guy here, we recall that we know now that we can, so the bra associated to this ket here will look like this. Remember, we complex conjugate and transpose. So this would be also sum over n of Cn star, An. Okay? Applied to sum over n Cn An. To be more general, let's call this one, sorry, rather M. Now, these are numbers, so I can put the numbers together, and I will have the bra here and the ket here that I can bring together as an inner product, scalar product. And the scalar product of Am, An would be 0 if n different than n, and it would be 1 because those are the eigenvectors, so they form a basis, we said, a normalized basis to 1. So in only one case, the inner product between Am and An will not be 0, is when m equals n. Okay? So if I do that, Let's do that here. I need something to erase first. Then I have this quantity, which is this quantity, which is sum over m, sum over n, Cm star, Cn, An, and inner product Am, An. And this is 0. For m different than n, and is 1 for m equals n. So if for n equals m, then all we have left is sum over n of Cn star, Cn An, which is sum over Cn squared An. And that is exactly what we wanted. Over there as well. So in general, this definition will be the definition of a mean value of an operator, which is what you're going to obtain on average when you make a measurement for a given operator in a given, with a system in a given state. Just a word on the integral formalism. Remember, we said that we can have, the physical meaning to this bracket can be seen in terms of integral of the wave function. Then what we see here is that, so if I write this, it would look like this with the rules that we said before. So the bra would be phi star, then A is in the middle, and then phi for the ket on this side. What is very important, though, is to leave the operator A where it should be, in between these two. You will see just after why this is important. And this is the mean value of this operator. And in fact, what this looks like is the probability, it's the mean value of a quantity A times a probability distribution given by this integral psi star psi over dv, dv being the volume or the integration of the whole volume in 3D space. Okay. So what we have here, and I'll come back to that in a second, is that we have really, so the mean value A here of this quantity, usually a mean value is given for a probability distribution. So in this case, the probability distribution is given by the wave function, or in terms of integrals, which is more physical meaning to it, would be the integral over the entire volume in 3D space of psi star A psi. Okay? Quick note, if we apply this rule here, so that we said here, to the spin, the electron spin, which has only two possibilities, either plus h bar over 2 or minus h bar over 2, then we will find that on average, the mean value is 0. Which makes sense because if your electron spin has a probability of being 50% up or 50% down, then on average the value is 0. So I'll let you do this quick calculation using the same formalism here. Quick word on the probability distribution that we define, I redefine here. I just want to say this is the equivalent to standard probability distribution, of course, that we have. For instance, here there is maybe one of the most famous one is the so-called Maxwell Boltzmann probability distribution, which describes the speeds of molecules in a gas. Okay, so there is a speed distribution, which is a function of the temperature. In other words, if you take a gas in a box, and if you heat up the box, then the gas inside the speed of the gas inside will increase. So if you take a balloon, you will see the balloon will expand as you warm up the balloon. So there is a probability distribution which for the speed, which is a probability distribution in this case would be a function f of the speed v times dv. This function f is given by this, so some numbers, whatever, some parameters, depending on t, of course, the temperature, but also exponential minus energy divided by kBt, where kBt is the so-called Boltzmann energy linked to the temperature. And Ek is the kinetic energy of the molecules in this gas, which would be simply 1/2 mv squared. So if I want to know now what is the mean speed of the molecules in this gas, then I would have to calculate this quantity, which is the integral of Vfv dv. Okay, so it's exactly the same thing as if you were to take the average of marks or grades given in a given school for a given exam, which is going to be soon. Then all we do is we take the average of this of all the marks by being the sum from I to n wi xi, where xi is the mark and wi is the weight you can give to each mark. So if you say, well, I consider with the same weight, if you have 5/20 or 15 out of 20, then what you have is simply the standard mean value, average value. But you could decide, and that's what we do, in fact, most of the time, to give some weight, to say, well, we can sort of shape a little bit this probability distribution, which is the case here. So here, what is plotted here is the probability distribution f of v for molecule speeds in a gas, for instance. So these are examples, but there are many examples, and in fact, what we have here is the same thing for the operator A, and we can apply it to the position operator, for instance, if we want to know what is the average position of your system. So it would be the integral of 5 star x psi. So that's what I wanted to say about mean value. Now, there is another aspect. I just mentioned that when you do that, the position of the operator, A or X, has to be in the middle here, has to follow this rule. And the reason is, and that leads us to a second very important properties in quantum mechanics, is that in quantum mechanics, operators or measurements do not always commute. So in other words, if you start from a wave function, from a quantum state psi, if you apply a measurement first, say A, and then B, you will obtain psi prime. In classical physics, whether you do A and then B or B and then A, you should end up with the same results. But that is not true in quantum physics. In quantum physics, you obtain a psi second, which might be different than the psi prime. So in classical mechanics, classical physics, psi prime equals psi second. No problem. So in other words, if I have an electronic circuit, if I want to measure the current and then the voltage, or the voltage and then the current, it doesn't matter which way I do it, I will find the same result for both. But not in quantum mechanics. In quantum mechanics, the so-called commutator, so this quantity, AB minus BA, can be 0, but sometimes is not 0. So in other words, the order in which you make the measurement do matter. Okay? And there is an example, which is the commutator of x and so position x and the so-called momentum. We define the momentum along the x direction, if you remember, is not 0. It's, in fact, is I times h bar. It's a quantity I times h bar. So it is not 0. So in other words, I already mentioned that before, and that's linked to the so-called Heisenberg uncertainty or Heisenberg inequality. It tells you that for a quantum system, if you want to know what is the position, and then what is the momentum, or if we want to know first what is the momentum and then what is the position, then you have an uncertainty on the result on the order you do that, which is on the order of the Planck constant h bar divided by 2. So this is not necessarily something that we will be using for quantum gates, for instance, but it's something to keep in mind in general in quantum physics, in quantum technologies. This will pop out at some point, is the fact that the order of operations and gates, so this order does matter. Okay, so you have to be careful by expressing the fact that when you do AB on psi, what you do is you do B on psi first, and then A on B psi. And that is not necessarily equal to doing A, applying A on, or measuring A on psi first, and then measuring B after. And you can see that the order is the closest to the ket to the further. We could have more. You could have D, C, B, A. Okay? So in other words, what it means is that you make that measurement first, then this one second, then this one third, and this one fourth, and so on. Okay? So the order is very important. And you can see now why in here this would be also important, because, well, here you have psi star, and here you have psi, so you don't have the same thing. Plus, this is sort of fairly easy in a sense that you only have one operator, but when you have more operators, it's very important not to mix around the order of operations. Okay, and so we define what's called the commutator between two. So the commutator between two matrices, two operators, as this AB, so we put it in brackets, being AB minus BA. Oh, there we go. Right. Okay. So that's what I wanted to say. One last point that we did not have time to cover last time is the notion of outer product that we already discussed. So the outer product, the inner product gives you a number, because we did say that the inner product in a way is a scalar product, so a scalar product gives you a number. But an outer product, rather than doing bra ket, you do ket bra. Again, the order matters. Will not give you a number, but it will give you a matrix, in fact. So let's take this example. So let's take psi phi. So psi phi. And let's take, so the ket bra this time, and not the bracket. The bracket is the inner product, but the ket bra is the outer product. So what does it look like? Well, if psi is alpha beta and phi is gamma delta, then the bra phi will be gamma star delta star and now I want to calculate that. Well, remember we in one of the lessons I said when we made these calculations, computations of matrices in columns and rows and things like this, that we said, well, let's stick to that rule of operations. Well, if we do that, then this should be a 2 by 2 matrix, because if I apply, then I multiply this by this, okay, but I can also multiply this by this, and I can also multiply this by this, or this by this. So when I do this by this, I will obtain alpha gamma star. Then I can do this by this, so that would be alpha delta star. Then I can do this by this, that would be beta gamma star, and then this by this, that would be beta delta star. So I've got a 2 by 2 matrix. And this is the outer product. So let's have a look at an example. If you remember last time we talked about projectors. I defined the projectors. So for an electron spin to be in the upper state or to be in the lower state, or to be spin up or spin down, or one way or the other. And in fact, now, so this would be the projector. So projector, so which is an operator. So the operator of projecting along up. And then this one would be the operator of projecting along down. Now, so these are matrices, these are operators, they are metrics. So now, if I can define P up as being the ket bra, up, sometimes people just make a cross here to be quicker. And that would be what? Well, that would be 1, 0, and 1, 0. So if I apply this, then this time, so it's a 2 by 2 matrix. So this time this is 1, this time this is 0, this time this is 0, this time this is 0. And I end up with this matrix. If I were to do the same for P down, I would obtain this one. Okay? And now to show you that this is the operation of projecting along up and this one along down, then I can, well, this is not this different. Then I can try. So let's apply it to our qubit, say alpha 0, the most sort of the more general qubit we can have. And now let's apply the projector up onto psi. So that would be this matrix. times this vector here in the vector notation, alpha beta. Well, so this is going to give us a vector. So this by this, alpha, this by this, 0. So we find alpha 0, which is projecting along 0. And if I were to do it for down, then I would find beta 1. Okay? Wow. So that's all I wanted to say for now for outer product. We may have to come back to it later on to define quantities that we may need at the later stage. But let's not worry about this for now. And also something that I did not do here is that we have to take care of normalization factors, but let's not worry about this for now. That was just to give you the idea of what an outer product is and a concrete example of outer products that gives us operators that can then be used on a given wave function. Right, so that's what I wanted to say from last time. There is one more thing I'm going to add though. That is, I promised that before, so today I'm going to mention very briefly how in the lab we can create entanglement. And then at some point I will actually show you, have a demo, a live demo on how to create entanglement. So there are many ways of creating an entangled state, but I want to show you how we create entanglement with photons, with two photons, how we can entangle the polarization state of these two photons. So for that, I need some physics, very basic physics or very sort of quick crash course on nonlinear optics. So this equation here, this seems to be a complicated equation, is nothing else than a representation of an atom, where if I take the simplest atom, I would have a proton and an electron for the hydrogen atom. And in a classical model, which is okay for some approximation, in a classical model, I will assume that my atom, given by this proton and electron, is simply these two charges linked by a spring, okay, and that the electron is attached to the proton by a spring. So if I do that, and then, so I take this atom now, and then I send some light, I put it in an electric field, and I make it move, all right? So what you have here, this equation here, in fact, what you see, and I'll write it here, it's that, let's get rid of everything, is nothing else than the Newton equation. So this is a crash course on nonlinear optics, but in fact, this can apply to nonlinear phenomena in a general way. So say we have the hydrogen atom, which is a proton plus an electron linked by a spring. So something like this, okay, with a spring constant K, and I'm looking at, so I apply Newton to the electron, and Newton tells you that the mass of the electron times its acceleration. So in this case, I will not use vectors. I will assume everything is in one direction along x, is the sum of all the forces, external forces. So in this case, there are only two forces. The first is the force of the spring, and the second is a so-called restoring force, which can be seen as a way of slowing down the movement. So in other words, when you take an atom, so and I forgot, you put this atom in an electric field. So if you put it in an electric field, there will be an electrical force that will apply, to this electric, that will apply to the electron. So this is the electrical force. So it's simply the charge of the electron, which is minus E, times the electric field, E, which we assume is dependent of time. The restoring force is going to be something on the order of minus gamma V, where V is the speed of the electron, and that is, this force is the so-called friction force. And this force is responsible for the fact that once you excite the atom and you leave it, so once you apply an electric field, the electron will oscillate, and then at some point it will stop oscillating. And that is thanks to this restoring force. And then you've got the spring force, which is something like a minus K spring constant times the displacement x. Okay? And this is the mass times the acceleration, and acceleration is the second derivative of x in time. And I've got everything here because V is simply dx over dt, displacement along x. So if I take this, I can rearrange it so that it will look like this. So I'm going to put the mass on the other side, so I will have d2x over dt squared equals plus k over me x plus, let's take the same order as it is in the slide, plus gamma dx over dt. No, here it's something like alpha, so it would be alpha over m e plus k over me x, and that would be equals to minus e over me e. Well, this in the slide is called gamma, doesn't matter, and this is the so-called frequency of the oscillator, which we squared, which we call omega 0. So this is the natural frequency of the oscillator, if you like. So this is it. That's the problem that we are given. Except that an oscillator, so a spring like this one, and you can see here on the slide, is that here there is a linear part, that's this one, but you can have an harmonic part. You can have higher terms for this oscillator. So this oscillator doesn't have to oscillate linearly, but it can have some more sort of extravagant movement. And that's what oscillators do. So you would have a second term, which we call an anharmonic potential, whatever the name, but you would have a second term here, which is basically a expansion, can be seen as an expansion, which would be plus a over x squared. So this is a non-linear term because it's squared. And this means that now the system, the medium, so if you have a piece of glass, for instance, with many of these atoms that look like this, then this piece of glass will have a nonlinear response in terms of frequencies due to light. So in other words, you can generate different harmonics of this oscillator. Namely, you can, if you start with an incoming electric field with oscillation omega, which is the wavelength, the incoming oscillation of the electric field, then you can come up with oscillations now that will be 2 omega, so higher order for this spring, nonlinear oscillations. So what does it mean? So it means that if I take a piece of glass, if I send light through it, like a window, then probably the power of the light, say the sun, is not strong enough to induce the nonlinear part. So in other words, what it means is that the light going through, the color of the light, the wavelength of the light going through the window will remain the same one. So if I have a blue sun or red sun, then it's going to go through my window and I will see blue sun or red sun. The frequencies remain the same, the colors remain the same. But now, if I take special glasses, special crystals, optical crystals, which have higher nonlinear terms, so where this part can be enhanced, and if I send more power, strong power, usually with lasers, then I can generate these terms. And these terms means now that when I come in with a certain color, say blue, or say red, then I can end up with twice the frequency of this color, which is half the wavelengths. So it means now that if I take a nonlinear crystal and I send powerful light onto it, red light, then some of the red light will go through, like our window, like the linear term, in a sense that it will not be nonlinear, but part of the light incoming will be transformed into a blue light of higher energy, of lower frequency. So higher energy means 2 omega, lower frequency means lambda over 2. So if I come up with a wavelength of 800 nanometers, which is close to the infrared, then I can generate some blue light or close to UV light at 400 nanometers that I can see with my eyes. So I generate different colors now by applying usually a strong incoming optical beam onto this nonlinear crystal with a high coefficient. So I can generate, we say, higher harmonics. So this, we do that in the lab every day. We have laser systems and so on. We use nonlinear optics every day, usually to generate different colors with different lasers so that we can use that in our lab for different applications in biology, in physics, in chemistry. And this is known since the 60s. It's called, so the easiest one is the so-called second harmonic generation, because you start from omega and you end up with 2 omega. So you go the second harmonic, you have high harmonic. You can also generate 3 omega or 4 omega, because they could be higher terms here. Okay, so we do that in the lab, no problem. Usually, and what we usually do is we take a piece of glass, which is a special glass crystal that is with a high coefficient, nonlinear coefficient, and we send strong laser beam onto it, focused, in order to generate these nonlinear terms, or to excite these nonlinear terms in order to generate higher frequencies, higher harmonics, different colors, and go towards the green, blue, UV, deep UV, and so on. Now, what is interesting is that if you do the reverse process, because the reverse process means what? The reverse process means that now you come up with a strong laser beam, but with a high energy, say a blue photon. Blue is usually higher than red. UV is stronger than infrared, to remember. So now you do the opposite. What we've done here in this experiment here is we took, say, red light and we generated blue light. In order to do that, we can go the other way, and in order to do that, we have to keep in mind that light is made of photons, and that also nature, whether it's quantum or not, there are still some rules that you have to follow. There are still some conservation quantities that you have to observe. And the two main ones are the so-called momentum conservation, there's a momentum conservation, and the energy conservation. So let's start with the energy conservation. Of course, the nonlinear process I just mentioned, I told you that with red light you generate blue light. So you could say, hang on, this is different energy, how you do that? Well, it's very easy, because what you do for energy conservation is that you add two, in terms of photons, you take two red photons that pair together in order to create a blue photon coming out of it. So the standard nonlinear process, so the so the one that we can do fairly easily in a lab, the higher harmonic process tells you that you take one red photon and another red photon, photon. So each of them would have energy, say they have the same energy, E1. So in the red, say for instance lambda equals 800 nanometers for these two photons. And we have a nonlinear crystal, and inside this nonlinear crystal, what we just said is that we create high harmonics, and basically there will be red light, but there will also be blue light. So we would have one blue photon with energy E2. And E2 would be what? Well, E2 will be twice the energy of E1, or rather E1 plus E1. Okay, so I do not create energy. I take some from the red light to transform it into the blue light. So that's what we do. So there's no problem with that. There's also momentum conservation, which means that the orientation of the photons, of the light inside the crystal, is also very important. But let's not worry about this for now. But now what's interesting is to do the other way. So I take the same crystal, and rather than coming with a red laser, I come up with a blue laser onto this crystal. So this crystal, for instance, this one is so-called a BBO crystal, whatever the name, is just a particular glass crystal that has a higher nonlinear coefficient. So if I do that, so using this crystal, BBO, same one here, I can, so if I use a red laser, two red photons will give me a blue photon. But now if I do the other way, I take the same crystal, but I come up with one blue photon, so blue photon, of energy E2. Well, this is to actually show that quantum mechanically is quite difficult, but it can be done. And what quantum mechanics predicts is that, and works, is that this blue photon has a probability, is very low, but it's not zero, and it's not the same probability as me going through a wall. So it's still something that we can measure. So it has a probability to split into two photons of low energy. One red photon here and one red photon there. Okay? So it's the exact reverse process of here, except that this can be extremely efficient. This is not efficient, unfortunately. So only one photon out of, say, 1 out of a million will get from one blue to two red photons. But now, what's interesting about these twin photons is that you created twin photons, photons that have been created at the same time and can have the same properties, so the same energy, for instance. But also, as you see on this graph, or by this rule, they also have momentum conservation. So momentum conservation is the direction of emission. So it means that momentum conservation tells you that these two plus this one have to equate, and this one and these two have to equate as well. Okay, so if the incoming photon, say Kp, P is for pump, because usually we talk about the pump laser coming in, then K pump will be equal to K1 plus K2, where 1 and 2, or let's call them 1 and 2, photon 1, so one red photon, photon 1, and photon 2, where K1 and K2 are the directions or the propagation vectors of the two photons. This is, by the way, a purely quantum mechanical process. There is no such thing in classical counterpart, where one blue photon spontaneously disintegrates and creates two twin photons of different colors of low energy. Knowing that, again, the energy conservation remains, like earlier. Now, these crystals, usually, they are what we call birefringent crystals. In fact, I showed you one at some point at one of the lectures where you could see this crystal rotating, and as you would see this crystal rotating, you would see one axis or two axes. And this is because this crystal is called birefringent crystal, and this crystal, so those are nonlinear and depends on the polarization state. So the light, the polarized light, will behave differently depending on the polarization state going through the crystal. So in other words, again, I'm not going into details, but that means that these two photons here can have orthogonal polarization. So one could be, say, H polarization. H polarization, so for horizontal polarization. And the other one could be V polarization. This is optical properties of crystals is known. There's no problem with that. We know that very well. So what we have here now, we have two twin photons with the same energy, with directions that are different, spatially different. One being with one polarization, one being with the other polarization. So now if I take this photon, so these photons, so let's assume that we have pairs coming out, then these photons will be V, and these photons will be H if I measure polarization state. And what you can show is that these photons, when they come out in two cones, actually. So in fact, if I were to represent that properly, there should be two cones like this. Okay? And these two cones of light, when the crystal is tilted in such a way that the two cones are well separated, then you end up with two circles like this. If I make a cut, so if I make a cut here, I end up with two circles which are disconnected. And if I measure the top one, I will find a polarization state, say vertical. And if I measure the bottom one, so any photons on this circle will be a horizontal state. So the state I will find would be, in terms of quantum state, would be H1. I think I'm going to have to use something else. So would be H1 V2, say, for photon 1, photon 2. And then I know that. I know every time I measure here, I measure V. Every time I measure here, I measure H. No problem. But now what's interesting is, that's what people do, is when you start to tilt slightly this crystal. And when you start to tilt this crystal, the two cones will come back, will get close to each other, and you will have these two circles which will crosses at 2 points here. Okay? So here you have a sort of color-coded version, so a cut. So these are actual photons coming out on the screen, pairs of photons coming out of the screen for different colors. And if I look at the green circles, I've got these two circles, okay, emitting these two cones, if I make a cut. And I have two intersection points, 1 and 2. Now the question I have is, what is the polarization state of this photon here and this photon there? Well, you don't know. You don't know that because what you know is that this one had, say, horizontal polarization for the top one, and this one, the bottom one, had vertical polarization. So here I know, and here I know as well. But at the intersection point, I don't know, because now this is mixed. So I could, if I measure one photon, I could find H or V. I don't know that. But what I do know, because the polarization have been mixed in a way, but what I do know is that when one photon is H, so if I were to measure H here, then the other photon from the pair, the other twin photon, has to have the complementary polarization V. And vice versa, if I were to measure V here, then I should find H here. And as I don't know what I'm going to find in advance, then that means that basically these two photons, these twin photons, are not twins anymore. They're more than twins. They are entangled in polarization and polarizations. Because now, if one is H, then the other one, so number 2, would be V. But we said that one could also be V, because it's on this intersection point. Therefore, the other one has to be H. So what it means now is that if I create these pairs of entangled photons, now I've got one photon here and one photon there, so I can take one, I can give one to you, and if you make measurements on your photon, you will find with a probability 50-50 to find H or V. But if I make the same measurement on my photon, which is the entangled one of yours, then I know for sure that if you measured H, then I should find V. And if you measured V, then I should find H. And this is an entangled state. So we do that for one pair, the next one. So after 100 tries, you would have 100 photons. On average, 50% of the case, so 50% will be H polarization, vertical polarization, and 50%, so 50 photons would be horizontal polarization. Likewise for me, on average, I will have 50 of them, 50 of the others. That is random, but what is not random is when we will look at each measurement for each tries of our twin photons, and we will find that they always complement each other. That always, if you found H, I find V, and if you find V, I found H. By construction, this is how they were constructed, and as we brought the two cones together, we have now two intersection points Well, we don't know which is which. So this state here, the state of the two system, will look like this. And this is an entangled state. If I remember, if I say H is 1 and V is 0, then I've got 1, 0 plus 0, 1. So it's one of the so-called Bell states. So I just generated psi plus or psi minus here. So I generated entanglement. And this is used in the lab every day. And in fact, recently, don't know if you heard, there was an article published by a Chinese group on, again, on this quantum supremacy using photons. And they used many photons, but they used the same technique. At the base, this is exactly what they used, except that they generated more pairs, entangled pairs, and put them together to have an algorithm. But they used exactly that. And this is this experiment. I will show you at some point live this kind of experiment and how we can generate those and how we can generate the so-called Bell states. Okay? So I wanted to say that because we will use... So this process, by the way, is called spontaneous parametric down conversion, or SPDC. So why? It's a very long-winded name. Why is it called like this? Well, spontaneous, because it's a spontaneous process. Like I said, unfortunately, this is not something we can control, which is a spontaneous process. One pair is emitted, and with a very low efficiency, unfortunately. Parametric in a sense that the properties of the two emitted photons are linked with each other in momentum and energy. And down conversion, because this time, as opposed to earlier, we started with an energy of, say, 2 omega down to twice omega. So we down converted the frequency. We went from a higher frequency to a lower frequency, as opposed to this process, which we can do very easily in the lab every day and is very efficient. We can convert up to 100% of the light, which is going from low frequencies to high frequencies. So that's an up conversion. This is a down conversion, okay? Because you down converted the light. And this is, unfortunately, not very efficient. But that's life. Right, so that's what I wanted to say. So now, can finally start the lecture of the day, which is on quantum gates. So as I said, there will be 5 parts, so definitely I will not finish it today, but I guess you gathered that by now. But let's discuss about 1 qubit gates, 2 qubit gates, and so on. So the first one, very important, is, so we said, you want to build a quantum computer, so you need qubits. Okay, so we know what they are, we know their properties now, we know how to generate them with photons, with electrons. We can use electron spins as well. Now, the question is, we want to make operations on these qubits, like we do in the classical world. We have operations on classical bits. We want to do operation, so on single qubits and maybe on more qubits, like 2 gates, like we do in the classical world with an AND gate or OR gate, like I mentioned during lecture number 2. So for 1 qubit gate, well, the first group of gates that we have is the so-called Pauli Matrices group that we already saw. So the Pauli Matrices are these 4 gates, which is the X gate, the Y gate, the Z gate, and the identity gate. And so the identities do nothing. The Z gate can be seen, so if we go back to the block sphere representation, we can see that the X gate is basically a NOT gate where you go from 0 to 1. So it's a rotation around the X-axis, and the matrix is given by this. The Y gate is a matrix given by this one, which is rotation along the Y-axis. And the Z gate is a matrix given by this, so 1, 0, 0, minus 1, and it's a rotation along the Z-axis, hence the names X, Y, and Z. So we can represent these X, Y, and Z operators, and those are operators, so those are things that we can manipulate onto the block sphere. Okay, so I believe you did some of that in tutorial work, and there will be more probably to come at some point. Just a quick word is that the Pauli matrices in all the different permutations, and they have, I'm not going to go detail that, but you can create, so sigma x, the product sigma x, sigma y gives you sigma z, and so on. All the permutation is basically, so the Pauli matrices are basically form a group in a mathematical sense, and this is called the Clifford group. Okay, so all the Pauli matrices and all the permutations of them is the so-called Clifford group. So there is another gate that is very important. So by the way, just to come back, oops, sorry, I went too far. Oops, no, this way. So for instance, remember the X gate, so let's practice though, is the NOT gate. So the NOT gate is basically reversing the qubit. So if I think we already covered that, but let's do that again briefly. So the X gate, if I apply it to my qubit psi, where psi would be the more general case of a qubit state, then I have so 0, 1, 1, 0 applied to alpha beta, and if I do the calculation of this, I will find beta and alpha, and that would be beta 0 plus alpha 1, and that is a NOT gate. Okay, and then the Y gate and the Z gate. This one is sort of more explicit because we can see that we reversed the coefficients, so we went from alpha 0 plus beta 1 to beta 0 plus alpha 1. So that's how you would do in practice. So that's you apply your gate to your qubit. Now the second another important gate is the so-called Adamar Gate, which we call H, which is different from the Hamiltonian operator that we touched upon and come back to it at some point. So the Adamar Gate, so here it is, so it's 1 square root of 2 for normalization, and then it's 1, 1, 1, minus 1. Okay, and this gate is the sort of superpositioning gate. So what do I mean? So, and this is the representation. So now, of course, every time that we start to see gates, we've seen those before, but we will see the representation in terms of circuitry, what the different gates look like. Okay. So for the Adamar Gate, this is the representation. And I can look at what it does to a qubit Q0, given to, the qubit Q0 and ending up with the qubit at the end Q. So let's apply. So I come up with the qubit Q0, and I apply the Adamar Gate. And assume that my qubit is originally in the 0 state. Okay, not the more general state, but in the 0 state. So, okay, so now I can apply this. That would be 1 square root of 2, 1, 1, 1, minus 1. And then the, so this one, let's assume it's in a 0 state. So that would be the vector 1, 0. So if I do that, then I've got 1 square root of 2, I've got 1, and I've got 1. So I end up with 1 square root of 2, 0, plus 1. So this is a superpositioning gate in a sense that I went from a given state 0 to a superposition 0 plus 1. Okay? And if I were to do 1, to start with Q0 equals 1, so that would be the Q here, the end result. So if I were to start with 1, then I would end up with 1 square root of 2, 0, minus 1. But again, a superposition state. Okay? So the Adamar gate is very important, and especially is used, as we will see, to initialize all the qubits from sort of a given state to a superposition state, so to a real or more general qubit. We have to notice at this point a very important property is the fact that the Adamar gate, like the Pauli matrices, like the Pauli gates as well, are what we call unitary matrices. So the definition of a unitary matrix is that H times H dagger equals the identity matrix. So if I take the Adamar gate and I multiply it by itself but daggered, so remember H dagger is complex conjugate transposed, then I should find the identity operator. And this is a definition of a unitary matrix. So in other words, H dagger is the reverse, is H minus 1, is the inverse matrix of the Adamar gate. That is the definition also, same definition, another way of writing it, of a unitary matrix. And this is very important because in order to do quantum computation, you need unitary matrices. The reason for that is because you have this inverse property here. That means that whatever you do as a computation to applying gates, you should be able to reverse it. You should be able to come back to it. The reason being that when you do your calculations, so when you apply your quantum gates, the last thing you want to do at the end is a measurement. But you remember, and we'll come back to that, that once you do a measurement, then the superposition is gone, right? If you were to be in a superposition state, if I measure, then I will find a certain probability 0 of being beta squared, or certain probability of finding 1, with a certain probability alpha squared of finding 1. I will find only one of the two. So the superposition is gone when I do the measurement. And that is because making a measurement is a non-reversible process. Because it's a non-reversible operator. Once I measured the result, that's it, gone. I've got the collapse, remember, the so-called collapse of the wave function, and I found the result. But when you do computation, you don't want that, because you want to maintain all the way, or at least during your quantum algorithm, you want to maintain superposition. So you want to use operators, gates, that do not make a measurement in a sense that does not collapse the wave function. It manipulates the qubit, but it doesn't, so we need that, we need to manipulate the qubits, but we should be able to reverse it back. Might be more complicated, but we should be able to reverse it back. The reason being is that so we can go from one to the other, again, from one transformation to the other, without actually collapsing the system when we're not supposed to. We only collapse the system when we make a measurement, and usually it's at the end. So I will show you later on. I mean, it's the same example as earlier. if I go back to this entangled state, these photons are entangled as long as I don't measure them. Of course, once I measured 1, you measured 2, we have collapsed the wave function to you find H and I find V, and you find V and I find H, but only one of the two. But before the measurement, we are in this superposition state. And we need to preserve that during all computations in order to be able to use a quantum computer and to use the power of quantum parallelism. We need to preserve that. For that, you need unitary operations, unitary matrices, which we usually call U, so the operator U with the hat, I remember, as a global or general unitary transformation, or unitary gate, or unitary matrix. Right, so let's carry on. So you can show, I'm not going to do it here, but if you take H and you multiply by H dagger, you should find identity. Likewise, you can do the same with the Pauli matrices, you should find identity. Oops, am I going too fast? Another gate that is used, you have to realize, I mentioned that depending on the system you use, so we talked about photons, we talked about electron spins, we talked about superconducting or trapped atoms and so on and so forth. So you have to realize that for different systems, not all gates are easily done. So for instance, I will come back to that as an example. The Adamar Gate in optics on single photons is very easy to do. What you do is you use a so-called beam splitter, where you have a photon and you send it to a 50-50 beam splitter. I showed you that already, so that you split the path of the photon. And the photon can be there or there, and it can be in this superposition state. So a beam splitter is a very good Adamah transformation, okay? Or a lambda over 2, so a half wave plate, which rotates, remember, the polarization state to 45 degrees is also a Adamah transformation in polarization. So in optics, it's very easy. But some other gates are not easy in optics, like the control knot, for instance, the 2 qubit gates I will talk about. So there are other gates, the so-called square root knot, or square root of x gate, which will look like this, which is a 1 qubit gate, but you can see a bit more complex. This is the representation. And why we call it square root of NOT gate is because when you apply it twice, you end up with the X gate, or the NOT gate. Remember, the X is basically a NOT gate. So again, depends on the system. So some physical system can implement the square root NOT gate more easily than others. There is another one also, that can be generalized to the so-called phase shift gates. So the phase shift is like the it looks like the identity gate, except that on the one that is here, you have an adjustable gate, adjustable phase. Okay. So, and these are names. So if the phase is pi, then you have the Z gate, because if psi equals pi, then we've got 1 minus 1, and this is the Z Pauli gate here. But if psi is pi over 2, then you have what we call the S gate, which is the square root of Z. And if you have pi over 4, you have the so-called T gate, which is square root of S gate, which is fourth root of Z gate, the Powerli matrix Z. So those are the phase shift gates are used in certain systems. And for instance, here I gave you an example of a superconducting qubit, in this case called a transmon, which uses the phase shift gates. So a transmon, in this case, is a capacitor, or two capacitors with a gate, and a Josephson junction, which we don't have time to go into that. And that in terms it looks like this, where you have two paths here and a Josephson junction in between. And you can show that with this transmon, this superconducting qubit, so these, remember I told you these sort of electrical circuits, this is an electrical circuit, the gates that you can make easily are the phase shift gates, for instance, okay? And this is something that maybe you are not be able to do so easily in other systems. So that's it for the 1-qubit gates, okay? So we've got few here. I didn't put the sign of the rotation gate, but it would be something like this. That would be the phase shift, sorry, the phase shift gate, not the rotation gate. Now, let's go to qubit gate, 2 qubit gates. And the first one is the inevitable control NOT gate or C0 gate. So a C0 gate is a 2-qubit gate. So if you remember, a 2-qubit gate is something that has a 4x4 matrix because it's basically the tensor product of the 2 qubits. So you go from 2 qubits to a 4-state qubit, meaning that you need now a matrix of 4x4 elements. So the C0 gate, which we write C0 or CX, it's a control NOT gate, meaning that it's a conditional, so it's a very important but very difficult 2-bit gate, which is a conditional gate. So so this is the symbol. So how does it work? So you have 2 qubits, Q0 and Q1. And what it does is that you usually have a control and a signal, or at least that's how we call it. And what it does is, depending on the state of the control, then you do something to the signal or not. So it's a conditional gate. Okay. So C0 gate so which we write like this, so in terms of circuitry. So let's say you have your qubit Q0, and then you have your qubit 1, and then, so this is the propagator of the qubit, and then you do a control NOT between Q0 and Q1. And you can see here the matrix representation tells you that, so one of them is the signal, that would be the signal, and that would be the control. And what it tells you is that if the control is in, say, the 0 state, then you do nothing to the signal. So if control is 0, then do nothing. So it's the identity. So now if the signal, so that means, how am I going to write this? That means signal, here. If 0, then you end up with 0, and if 1, then you end up with 1. And any superposition state, so if Q1 is in a superposition of 0 plus 1, then you leave it that way. But now, if control is in state 1, then you reverse Q1 signal. So that means that, and this is this part here, these sort of 0, 1, 1, 0, here it looks like the identity, do nothing, and here is the reverse. So if 0, if you started with 0 here, then the signal becomes 1, and if you started with 1, then the signal becomes 0. So this is a conditional gate in the sense that depending on the control, you change or not the signal. So it's a very, very important. It's a very, very important 2-qubit gate which performs a NOT operation, so reverse operation, on the second qubit, depending on the first qubit, and otherwise, so if first qubit is in a 1 state, otherwise leaves it unchanged. Okay. We can generalize this. So we can generalize this control NOT to a control U gate, where U is a unitary matrix. Remember, I wrote it earlier. So this, the C0 is in fact a particular case of this one, where this, so of this U operation, where this U operation would be, in more general case, a 4 terms unitary matrix, so U00, U01, U10, and U11. And U, this operator U, can be any of the 3 Pauli matrices. So in the case of Cx, then this is the C0 gate, this one. If U is Y, then this would become the so-called CY gate. And if U, so this one here, is Z, then this would become the CZ gate. Okay, so controls X, control Y, control Z, and the C0 being a particular case of the control X gate. Right. So why is this one so important? Well, because you can show that if you want to build a universal quantum computer, so a universal quantum computer, as opposed to different types of quantum computers that are more specific to some particular problems, a universal quantum computer is a computer that, hence the name, can do any computation. And in order to do that, all you need are basic gates, like we saw in the classical case. If you remember, there was a definition of primary gates, which were AND and OR and so on, and NOT. And it's equivalent for quantum computing. If you want to build a universal quantum computer, so a more generic quantum computer, all you need are these gates. So the Clifford group gates, so basically the Pauli matrices, the Adamar, the C0, which is a 2-qubit gate, and the T and S gates, okay, and a set of those. So with those, so basically with the C0 gate and the Adamar plus Pauli matrices and a mix of those, you can build a quantum computer. So you don't need that many complicated gates, as we will see after, to build a quantum computer. Of course, like I said, it's not so easy. In particular, the C0 gate is a very difficult gate to implement experimentally. Some systems do it quite nicely, some don't. And usually the ones that do it quite nicely, then they are the ones that are complicated to control on a single qubit level. So there is always a trade-off between have a nice 2-qubit gate or a 1-qubit gate. Having both at the same time is very difficult. But this is what people are trying to do, and it works all in all. And this is what people are trying to implement to have better gates for 2-qubit gates and 1-qubit gates. So more 2-qubit gates, 2 more. So the so-called swap gate. So the swap gate, well, you can see here, you start with 2 qubits, Q0, Q1. So this is a representation, or this is another representation, which is sort of clearer in terms of swapping. And then you take them, and then you swap them. So Q0 becomes Q1, and Q1 becomes Q0. You can show. So again, so please take the state Q0, Q1 in a more general, and apply the gates, the swap gate here, which is this one, where you can see the swapping is in the middle, and see if you come in with this state, if you come out with this one. For some physical, so this one, the swap gate, is not so easy to do for some systems. And in fact, for some other systems, what is easy to do, easier, is the so-called square root of swap. Again, this same idea. And the square root of swap gate looks like this. It's a bit more complicated. And we represent it like this. And why we call it square root of swap gate is because if you apply this one twice, then you end up with, so you half it, and then half it again, you end up with a complete swap. Okay, so again, depends on the systems. Some systems like that better than others. Right, and that's it for two qubit gates. Basically, these are the main gates that we have to deal with to experimentally prepare, control, and that people can use to build algorithms and various for various applications. There are more than 2 qubit gates, and I only mention 2 gates, although I'm not going to mention the use of it because it's rather complicated and rather technical. But it's good to know what they do exist and that they have the importance on their own. So the first 3 qubit gate, and again, the idea, so it's interesting because you can see, as we said before, it goes at 2 to the power of n. So now n equals 3, so we have 2 to the 3, which is 8 matrix. So we have an 8 by 8 matrix to deal with now. Okay, because we have 0, 0, 0, 0, 0, 1, 0, 1, 0, etc., etc. If you remember the lecture number 4 on multi-qubits, then when you have 3, you would have an 8 by 8 matrix because you would have an 8 vector column, 8 number vector column. And the Toffoli gate is basically, so sometimes it's called a control-not gate. Okay, and that's the representation. Because the control-not gate, you can see everything only happens here, does that if the first 2 qubits are in the one state, then you apply the Pauli X not, the Pauli X or not gate to the third qubit. If it's not the case, if the 2 qubits are not both in the one state, then you do nothing. That's the rest of the matrix. So that is called a Toffoli gate, and it has its own importance, especially because it's linked to the classical equivalent of a Toffoli gate. And this is important when someone wants to talk about reversible computation and compare the quantum and the classical part. Then the second one, a 3 qubit gate, is the so-called Fredkin gate, which is important for the same reasons as the Toffoli. And this is called a control swap gate on 3 qubits. So this is the representation. And you can see here there's a control swap given here. So again, the same idea is that you don't do nothing for most of the time, and then once you have 2 qubits in a certain state, then you swap with the third one. Okay. Right. That's all I wanted to say on 3 qubit gates, because those are, again, quite sort of technical. But they are interesting, and people are working on them. And also, again, it depends on the systems that, physical system that one can implement, because some systems can do those gates sort of fairly easily. And I put lots of brackets here. Right, so this is it for quantum gates. Now, how about we put them in a circuit? Well, there are some rules to apply. So the first rule is how you apply gates in series. So what I mean by that is that you have, so you start with your qubit, okay, so you have to follow, so the picture is like the line, so you follow the line, so the qubit follow the lines, and then everything, so here's identity, so you do nothing, so it's evolution in time, so you don't do anything, and then at some point, you come up with the gate. So here's a C0 gate. You can come up with the Y gate for Pauli, and then an X1. So here, it's a gate in series because you apply first Y and then X. So you apply the so-called dot product, the multiplication product of the two. But what you do is, so you remember, as this one comes before this one, you remember in terms of applying to a qubit, we put it first. So y is applied to phi first, and then x is applied to, so you see here, to the result of x and y, of y and phi. Okay? So this would be the dot product, and this would be what it does. So you apply one gate, the y gate, and then the x gate afterwards. So in essence, what you do is you take psi, you apply the Pauli X gate first, and then the Pauli X gate second. So this would be in series, but you can work in parallel. We said this is how you make multi-qubits, and you need that in order to build your quantum computer and to make use of this parallelism of having matrices growing up as 2 to the power of n. So for that, you have two qubits, psi and phi, and you apply the gates, so y and x on each of them, and that is equivalent to the tensor product, the cross product, the famous tensor product that we already talked about. And this is equivalent to doing x cross y on psi cross phi. So in other words, that means that the tensor product, if you remember, we saw them for vectors where we multiply. So we multiply. So this we know. Okay, we've done that before, where we went from a sort of alpha beta and gamma delta to alpha beta gamma delta to a 4. So 2 times 2 to a 4 column vector. But we didn't see that for matrices, but for matrices it would be the same. So for matrices, if you take y and x, what you do here with these two qubits is you do the tensor product of x and y. So if you do that, well, you apply the same rules as we saw before for vectors, but to matrices. So 0 minus I 0, tensor product with 0, 1, 1, 0, will give you this one, when you follow the same rules as before the tensor product, which is going to give us this new 4x4 matrix. And this is what you're going to apply to this state, which is the state. Another way of writing it, if you remember, is this, which is the tensor product of psi and phi. So this is how you treat gates in parallel. This is how you treat them in series, and this is how you treat them in parallel. In parallel, you have to do the vector product. Sorry, the tensor product. Let's have a look at an example. Let's have a look at the so-called superpositioning operation. The proper name is the Adamar Transformation. So the Adamar Transformation, remember the Adamar matrix is something that can take a state and put it in a superposition state. So the good thing about Adamar is that if you apply it in tensor product to different qubits, so if you have, so say you start with a qubit 0, 0, 0, 0, 0, 0, well, if you have it n times, you can apply Adamar n times and create the tensor product h to the power of n, which will tend to create an entire superposition state of all the different qubits, the n qubits together. So if I take the example of 2 qubits, so if I look at the tensor product of the Adamar matrix, so I do now the tensor product of Adamar with itself. Okay, so this would be the tensor product. I follow the same rules as before, and I end up with this 4x4 matrix. So you can show that for this matrix, now if I apply this new matrix, which I call H2, to the state 0, 0. So 0, 0 would be these two qubits being in the 0 state, initialized state, and I want to put them in a superposition state, on an entangled state. Then for that, I apply this Adamah transformation, H2, to my state 0, 0. 0, 1, 0 being so 0, 0. In this case would be Q0, Q1. Okay, and I apply H2 to this state. Well, if I do that, so I multiply this matrix times this vector, so 1, 0, 0, 0, 0, and I end up with something that looks like 1/2 of 1, 1, 1, 1, 1, of 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. So here we go, applying this state, so you do the calculation, and you will find that the state you end up with is something that looks like this. Which is a superposition state of all the 4 possibilities for the 2-qubit state. So that's for 2 qubits, but I can do it for n qubits, all in a 0 state, and I can end up, so if I perform this Hn transformation, with the superposition state of all the different combination of all the n qubits. Okay? So the Adamah transformation is very important on a n qubit register, because it gives it sort of in a so it starts from a known state, so say 0, 0, 0, 0 initialization, to a superposition state. And then you can start your parallel computing with it. Right. Practical cases. So I want to mention 2 practical cases. What I mean by practical cases is that I want to start from qubits, 0, 0, 0 here, and I want to end up with one of the Bell states, say this one, psi plus. So the question is, what quantum circuit, what quantum gates do I have to do in order to go from these 2 qubits, which start at this state, 0, 0, and end up with this 2-qubit state, which is in a Bell state, 0, 0 plus 1, 1, divided by square root of 2. Well, you can see it here. I need 2 things. I need to apply Adamah operation and then a control NOT operation. So if I do that, I end up with this. So we don't have time to do it today, so you can have a look. We'll finish that next time. And the second practical case, I'll just mention it, is the case of quantum teleportation. And quantum teleportation, so well, you know what quantum teleportation is to go from one place, say a spaceship, to a planet to visit, and being teleported from this place to this place, so from this teleporter to the planet by teleportation. So you disappear from here, and you reappear from there. So in quantum mechanics, quantum physics, you can do that. You can do that, especially with qubits. So we will see that the scheme you need to have is that you have your qubit to teleport here, and you want to teleport it there physically. For that, you will need a source of entangled qubits, A and B, and have to do an operation between A and C so that this will transform B automatically into C. Well, pretty much automatically, as we will see. So basically, you come up with one qubit, C, and that you sort of entangle with A and B, which are already entangled themselves, and basically transform the qubit properties from C to B, and B becomes C. So that's the principle of teleportation. And you can see, well, we'll see through that, but at the end, the circuit you need, so you need 3 qubits in this case. You need the qubit to be teleported. You need 2 qubits for entangled qubits, A and B. And so this is what the actual quantum circuit look like. So you've got C, A, and B, and you have to do Adamar, C0, C0, Adamar, measurements, operation, and then you end up with C being measured here, so being destroyed here, and I'll come back to that. It's important that the original state is destroyed, because in quantum physics, there's non-cloning theorem that tells you that you cannot clone a quantum state. So this state is measured and therefore destroyed. We said quantum measurement is irreversible. But this state has been transferred to this one, and this one now is the new C state that we wanted to teleport. And this is the quantum circuit you need for that. So we'll come back to that next time, which will be in a few weeks' time. So next week is, as I said, my colleagues from KED, so it won't be live, but the video will be available on our YouTube channel, UTT YouTube channel afterwards. It'll only be live for our students, same time, 10 to 12. Then 2 weeks break, and then we come back again with me. We will carry on this and carry on with the first small algorithm. In a way, this can be seen as a small algorithm, but we will see a bit more algorithm and how powerful they can be. And with this, I thank you for your attention, and I see you next week for the introduction and the weeks after. Thank you.